later when I would like to use it, a bunch of these coins show up in the ledger, statements of this kind with the associated coin commitment value. And later when I will eventually want to use it, so, well, if I didn't care about anonymity, I could just say, well, I'm using up some coin with a unique serial number. I expose the serial number, and now everybody can check that I haven't exposed the serial number before, so the coin is not double spent. And moreover, well, I show its CM and let everyone check that this CM is indeed in the list of previously published CMs. So that is sufficient to make sure that the only coins that are spent are the ones that were minted. But of course, it doesn't give any anonymity because when I spend, I reveal the serial number, and I reveal the CM, the coin commitment. In revealing the coin commitment, lets everybody associate that spending with the original minting that declared that CM. So there is no anonymity whatsoever. And therefore we need a different trick. And here it is. What we do is we take all of those coin commitments in the ledger that were created using these mint transactions. We create a Merkle tree over them by applying a collision-resistant hash function in the tree structure. There's a root. This is all public information. Everybody knows it. Everybody knows what the root is. And now I make the following statement in my spending transaction. I say I'm using the coin with a unique serial number that I hereby expose. So the serial number now became public information. And I also claim that I know a coin commitment in the tree, and I know an R that matches N. But otherwise, I know some CM such that SN and R map to CM, and CM is in the tree, but I don't show which one. And that would actually be an anonymized version. Now, what does it require to convince you of that proof? This small virtual accountant, this is the first example we see of that, requires several properties. Well, first, it should really be a convincing proof. Let me relax that notion a little bit for efficiency reasons, and instead of a proof, I'll make what cryptographers call an argument, which is a computationally sound proof. It's a proof that an infinitely powerful cheating prover might be able to subvert, but any efficient prover, any practical one, will never be able to falsify. So I want an argument for this statement. I want it to be non-interactive, so I can put it in the ledger, right? Proof systems can be interactive. That's not any good for a distributed system. We want it to be something we can just post on as part of a posted transaction, the ledger, and be done with it. We want it to be zero knowledge, in the sense that even though people are convinced that CM is in that tree, they have no idea which entry in that tree it is. It does not reveal any knowledge about the statement other than its truth. We want it to be what's called a proof of knowledge. And that means it's not just that there exists a coin commitment, but I know which one it is. And that's important to make sure that the security really goes through. And lastly, we want efficiency, succinctness. We want the proof to be small, we want it to be efficiently verifiable. So these are the proofs the properties that we need. It's, each one of these is necessary for the construction, and they all taken together they suffice. And taking this acronym, we call it ZK SNARK. That's the name of the cryptographic primitive that formally captures these properties. And ZK SNARKs have a glorious history. Let's start with recent history. These are not the first time they came up, but this is currently the most effective branch for constructively building them. So one kind of ZK snark are what's called pre-processing ZK snarks. Those are the ones that need that big public parameter file. And they're pretty new. The first one was proposed just a few years ago by Groth. Then there was a series of papers founding a theory of how to build them and what assumptions they can be constructed based on. And just the last couple of years, there's also been a flurry of activity on implementing them. Reinvoking systems that create zero-knowledge snarks for very expressive classes of statements. In fact, all statements in the NP language, but otherwise all computations that can be done efficiently using even knowledge-manipulative device. And to give one example, so this paper called Snarks for C show the system that lets you verify any C program. It takes any C program and compiles it using a customized GCC compiler into one which doesn't just, so the final program output by the compiler doesn't just produce the output, but also produces a proof that the output is correct. The proof is less than 300 bytes long. It takes a few milliseconds to verify, and verification was demonstrated on a cell phone in a live demo on stage in Crypto 13. So it really works. Those are the systems that we build on here. These systems do have the drawback of having that trusted public parameters or system parameters generation, which we'd really like to get rid of. And in theory, we know how to do that using probabilistically checkable proofs. These do have a much longer history. So Mikali in '94, following the work of Kilian, first showed how to use PCPs to create what we can now call snarks. The PCPs themselves have hundreds of papers in their construction, and to date, most attention has been mostly on very theoretical perspectives. Polynomial time existence, asymptotic properties. There is one recent paper that tackles more practical efficiency, and we believe that within the close future, we will see these coming to fruition and providing an alternative that removes the trust problem. Now, you may notice that several of these papers have author names that are familiar from the first slide, despite my watching of its presentation. And that's not a coincidence. In fact, we have a large project called Skipper Lab for sync computational integrity and privacy research, collaboration of Technion, MIT, and Tel Aviv University. And part of the slides that cut off says that if you go to skipper-lab.org, you can see all of these papers and read more about the underlying technique. And the reason I'm emphasizing this is that these underlying techniques are very general, as suggested by Snarks for C, and we'll be discussing some other potential applications for them beyond ZeroCash. Specifically, the snark that we used in ZeroCash is from this paper. This paper actually shows the high-level functionality using a virtual processor, running machine code and verifying it. What we did is take that, the underlying snark, which is the latest and greatest, and I'll show you shortly what we did with it. So actually, questions so far about snarks before we go back to ZeroCash? Yep.
So the parameter generation, if it's deterministic from the source code of the C program that's running on the snark generator? Or is there, so like, if we both, so I have to trust that the parameters were generated correctly. If I had the source code, could I verify that I came up with the same parameters?
So the question was whether the parameter generation is deterministic and therefore verifiable. Unfortunately, it's not. It's randomized, and actually that's why it's trusted. No one must know the randomness.
I mean, is that, are you going to have a multi-party generation of that? Can you like put 20 parties in such that and only one is needed to be trusted, or how does it work?
Indeed, one way to do that would be to have a multi-party computation that can be done using protocols that for which security it suffices that a single person is honest.
We'll get there later in the talk, but these are great questions, and indeed something like this should be done using the current technology.
And could you just repeat again, this PCP-based snarks should be able to remove the need for that 1 gigabyte file, but not necessarily soon enough such that you're going to use it immediately, is that right?
So the PCP-based snarks will eliminate that public parameters file. There will not be any big static file or any key whatsoever, just the description of a suitable field and the code itself.
But I mean, apparently it's not quite polished enough so that you could use it immediately in ZeroCash. Is that correct?
It's not ready for immediate deployment, no.
Okay, so going back to ZeroCash. So we started with some very modest requirements that look like this, just a single commitment. But I just told you that we can create zero knowledge proofs for arbitrary NP languages, for arbitrary C programs. So let's get greedy. Let's start doing more. Let's flex the muscles of the ZK snark to make the virtual accountant work harder and check more sophisticated properties and therefore give us more functionality. The first thing to do is to add, okay, you know what, let me take a few seconds to try to fiddle with the projector. I think it will help us through the rest of the talk. Anyone, if there are any other questions? Okay, that's more like it. Sorry for that. Okay, so here's what we're going to do. We're going to add values to coins. Every coin will have a value denoted in Satoshi or whatever your favorite currency is. Let's call it V. And when you create a coin, you will now need to declare that value. And that value will go into the commitment, producing the coin commitment. Now, another change that we'll have to do, and you'll see momentarily why, is instead of having the serial number go straight into that commitment, we're now going to have another intermediate commitment. So the serial number is committed into a value k, using commitment randomness R double prime, that gets committed into the final CM using a commitment randomness R prime. Now, to mint a coin, to convince you that I indeed correctly created such a coin with the right value, I just reveal the value, and I reveal this intermediate commitment k and the commitment randomness R prime, and I say, look, here's a CM, and if you just do this part of the computation, you see that the V, K, and R prime that I gave you are consistent, so you can believe me that this CM is a commitment to stuff that contains the right value. Therefore, I can now spend, burn, consume V bitcoins and V satoshis, and in exchange with CM that captures a ZeroCash coin with the same value V. So there's a one-to-one conversion rate between the underlying Satoshi Bitcoin currency and this value V.
Okay. So now how do I spend this? To spend this, well, I could just reveal everything like before, but that would not be anonymous. I would like to do it in an anonymized way. So what I do is I'll publish in the ledger a transaction saying that I'm using GAP, I'm spending some ZeroCash coin with value V and a unique serial number that I now reveal. And moreover, well, I want to say that this V and serial number are somehow related to a CN that appears in the ledger as having been minted. And the way I do this is by convincing you that I know R prime and R double prime. Please ignore these two letters. So I know R prime and R double prime. That suffices to convince you that CN indeed contained V, so it's the right value, and SN that that has not appeared before, so it's not double spent, and it doesn't reveal anything else by virtue of being zero knowledge. Again, I'm using a zero knowledge snark for that. Moving on, I would like to add additional functionality, and that is adding direct anonymous payments. So now that I have coins of variable denomination, and I can spend them myself, I would also like to be able to directly send these coins to someone else so they can spend it. And that would let me create a whole currency that